In this section, we're going to go over Gauss's law. And to apply and use Gauss's law, we're going to apply and use the electric flux equation. So, the equation for Gauss's law is equal to E, the electric field, at a certain point, applied over a certain point on the surface area of an object. And this funny looking circle right here is like the bounds of the object, and represents applying this equation over the entire surface of an object. And this is equal to the charge enclosed, Q enclosed, of the volume over sigma naught. Now sigma naught we know is 8.85 times 10 to the negative 12 coulombs squared newtons per meter squared. And this equation is equal to electric flux. You may be wondering, why do we have two electric flux equations? We do because this is the electric flux for a plane. This is the general formula. So let's apply this equation. We have a sphere. With a charge enclosed. And we have field lines leaving the sphere from the charge. So we're going to apply this equation. The integral symbol dA, if we are going to have the same electric field at each point on the surface of the object, which on your test you most likely will, and all the problems you most likely will. This integral symbol dA is the area, it's the surface area. And then E will just be a constant if the electric field is constant along the surface. So we can apply the equation E, the electric field, which is constant along the surface because everywhere along the surface is equidistant from the charge, times 4 pi r squared. 4 pi r squared is the surface area equation for a sphere. R, we know, is radius. And this is equal to the charge enclosed within the sphere over sigma naught. Solving for E, the electric field of the sphere, we get it is equal to charge enclosed over 4 pi r squared times sigma naught. Sigma naught we know is this number right here. And this is the electric field at the surface of a sphere. Now, we're going to do another equation. In this example, we have a wire, a long wire, with a uniform charge. And we're going to draw an example imaginary cylinder around it. And we're going to have electric field lines leaving this and passing through the imaginary cylinder. Now I'm going to draw this imaginary cylinder again so we can define some constants. R, which is the radius, and L, which is the length. So we're going to apply this equation. E is once again a constant because every portion along the cylinder is equidistant from the charge. And in this example, we're not worrying about either of the faces, only the cylinder area. So E is a constant. In the surface area of the cylinder, we know that the circumference of a circle is 2 pi r. And then the surface area of the cylinder is 2 pi r L, because it's the circumference applied over a length. Now we need to figure out what the charge enclosed is equal to. Lambda, which is equal to the positive charge per unit length of wire, so it'll be coulombs per meter, charge per meter. We have lambda, which we just defined right there, times length, and that is equal to the charge enclosed. So let's say we have a 4 meter long wire, and each meter is 2 coulombs. We'll have 8 coulombs enclosed. 2 times 4 equals 8. So that's charge enclosed over sigma naught. So we simplify this equation, and we get that the electric field at the surface of this imaginary cylinder is equal to 1 over 2 pi r lambda over sigma naught. And this is the electric field at the surface of the cylinder. Now I'm going to mention one extra point. If Gauss's law is applied within a conductor, which means that the electric field equals 0, then we will receive 0 for our answer, because there is no field inside the conductor.